Hello and welcome back to Homework Help for Math 2. Today we're going to be looking at Unit 4, More Functions, More Features, Lesson 4, Absolutely Transformed. In the Ready section, we're being asked to solve each of the equations for the indicated variable. So we want to isolate that variable. So the first assigned problem was number 1. So 1 says solve for x. So what that means is my goal is going to have x equals something, right? As long as x is by itself, that's what we're looking to do. So for number 1, we've got 5x minus 15y equals 20. So in order to reach our goal, we have to sort of deal with that 5 that's on the x, and we have to deal with the negative 15y. So the first thing that we're going to do is we're going to add 15y to both sides. And when we do that, the minus 15y and the plus 15y on the left are going to cancel. And I'm going to be left with, I'll do it over here on the right, we're going to be left with just 5x on the left-hand side. Equals, now we have 20 plus 15y. The order that you write these in doesn't really matter because addition is commutative. 4 plus 7 is the same as 7 plus 4. So the order doesn't really matter. It's like a quasi-mathematical convention in this situation that you would actually start with the term that has a variable in it or an unknown in it, and then you'd put the 20. If you put 20 plus 15y, that's not wrong. But you would more likely than not see it in this form in, like, say, a textbook or something like that. Okay, we're close to our goal. Now we all only need to deal with that 5 that's on the x, and it's 5 times x. So what I want to do is I want to divide, and that means I have to divide this entire thing by 5. Right? Because I want to divide by 5 on the left to get rid of the 5, but anything that I do on the left, I have to also do on the right, which means I have to also divide the right by 5. So on the left, I have 5x divided by 5. Well, those 5s go away. That's the whole reason I'm doing this, and I get x equals. Great. If I finish out the right-hand side, I'm done this problem. So I have 15y divided by 5. Well, I'm going to divide my coefficients, and 15 divided by 5 is 3. So it's 3y. That y doesn't go away, just 15 divided by 5. Plus 20 divided by 5. Well, 20 divided by 5 is 4. So I end up getting a final answer of x equals 3y plus 4. Next assigned question was number 3. This time we want to solve for x, and our equation is y equals negative 3x plus 12. This looks kind of like the slope-intercept form of a linear function. And in this particular scenario, we, for some hopefully legitimate reason, want to solve for x. So that's fine, we can do that. The very first thing I'm going to do, and this might not be how you do this, but for me, it says solve for x, and x is on the right-hand side. I don't know why that bothers me. So sort of like step 0 here, before we really do anything, is I'm actually just going to flip this. I'm just going to say negative 3x plus 12 equals y. I didn't really do anything. I just, obviously, when you have an equal sign, the order doesn't really matter which one's on the left, which one's on the right. But because I'm solving for x, I kind of want the thing that I'm solving for to be on the left. Because, again, we want our answer to look like x equals something, right? So, all right, so now we have negative 3x plus 12 equals y. In order to get to our goal, we've got to deal with the negative 3, and we've got to deal with the 12. And the first thing that we're going to do here is we're going to subtract 12 from both sides. By doing that, the plus 12 and the minus 12 are going to cancel, which means on the left-hand side, I'm now left with negative 3x, so I'm getting closer to my goal, equals, and I have y minus 12. I'm just going to leave it as y minus 12. All right. The only other thing that I need to do here in order to get x by itself is I have to deal with that negative 3. And again, the negative 3 and the x are being multiplied together, which means if I want to get rid of it, I want to divide by negative 3. And anything I do to the left, I have to do to the right. So on the left-hand side, I have negative 3x divided by negative 3. Well, negative 3 divided by negative 3 is 1, and then the 1 is my coefficient, just kind of goes away. It's an invisible 1. So I end up getting x equals. Great. Now, on the right-hand side, we've got y divided by negative 3. Now, there's a couple different ways that you could write this. The way that I would write this, and you might see a different format in a different textbook or whatever, but for me, I know that there's a 1 in front of that y, and so do you, right? We all know that when there's, quote, no number in front of a variable like this, there actually is a number, it's just 1, and we typically don't write it, but it is there. The reason why I'm drawing attention to that right now is because when we take y and divide by negative 3, well, the y is your term, but then essentially what we have here is we have 1 divided by negative 3. And 1 divided by negative 3 is just, it's 1 divided by 3 with a negative in it. So I'm going to pull my negative out, and then I have 1/3. So I have, let me just rewrite this now a little bit cleaner. So this becomes negative 1/3 y. So I would encourage you, if that didn't make sense to you, go back and take another look at it, and come to office hours if you're still stuck. But when you divide y by negative 3, you get negative 1/3 y. My second term here is the minus 12, and we're taking negative 12 and we're dividing by negative 3. Well, a negative divided by a negative is a positive, so this is going to be plus something. And specifically, it's going to be 12 divided by 3, which is 4. So this is our final answer. You could also potentially see it in this form. You could also see x equals something like negative y over 3. They just kind of they got rid of the 1, and then they moved the y into the numerator, and then plus 4. That would also be acceptable. I think that the first version is preferable, but the second one is not wrong. All right. Number 4, solve for h. All right, so again, our goal is to get h equals something. And our equation is a equals 1/2 bh. Hopefully, I think I mentioned this in a previous lesson not that long ago. Hopefully, you actually recognize this formula as being not just a bunch of random letters and numbers, but actually referencing something. This is the formula for the area, capital A, area of a triangle. 1/2 base times height, or base times height divided by 2. So you obviously don't need to know that for this question. However, I do think that there's value in sort of recognizing that these are not just like a bunch of random letters and numbers, but they're actually based in something. In this case, it's how to find the area of a triangle. So solve for h. Again, just like the last problem, I'm going to, my step 0 is actually just going to be to flip this. 1/2 bh equals a. Just because I want the thing that I'm solving for to be on the left. Not strictly necessary, and if you don't do that step, it's actually fine. But for me, I find it easier to have the thing that I'm solving for on the left, and then just sort of see how everything shakes out. So in order to get h by itself, we could treat the 1/2 b as like one thing, and then just sort of deal with it in one step. but I wouldn't recommend it. I think it's going to actually be easier if we treat the 1/2 and the b, if we deal with them sort of individually. So in order to get rid of the 1/2, well, technically we have 1/2 times, b times h, which means if we wanted to get rid of the 1/2, we could divide by 1/2, right? That is mathematically valid, and we could do that. We could divide by 1/2. But dividing by a fraction is kind of weird sometimes, and it might throw people off. So I actually think that an easier way to get rid of the half is actually going to be to take my entire equation here and to multiply by 2. All right. So mathematically, multiplying by 2 is identical to dividing by 1/2. It's kind of like, if you think about it, multiplying by 1/2 is the same thing as dividing by 2. I think that's kind of maybe easier to see. But if you flip everything, it actually is still true that dividing by a half is the same thing as multiplying by 2. I just think that this is going to be a little bit easier to sort of see, because when I multiply the left, I get 2 times 1/2, which goes away, and I'm left with just b times h on the left-hand side. Whatever I do to the left, I have to also do to the right, and so I have a times 2, which is simply 2a. All right, we are close to our goal. The only thing left is to deal with that b, and it's b times h. So here I am actually just going to divide. So we're going to divide by b. And when I divide by b, the b's on the left cancel, bh over b, and I get h equals. All right, that's my goal. On the right, we have 2a over b. Well, I can't really do anything with that, right? The 2, the a, and the b, they're all just going to sort of hang out where they currently are. So it actually turns out my final answer is simply 2a over b. Moving on to the set section. First set of directions say, use the given information to write the indicated form of the function. All right. And first assigned problem is number 8. So we are going to, it says, use the given information. So the given information for 8 is the graph. So we are given a graph of a function, and we're being asked to write it in the indicated form. The indicated form is an absolute value equation. So we're basically looking to convey the same information, right? The graph and the equation are mathematically identical. Obviously, they look different. One's a graph and one's an equation, but they actually are going to convey the same information. So we want to take this information that we've been given, which is a graph, and write it as an equation. So we're looking for an absolute value equation. So f of x. And there's a couple different ways that we can do this. I think the easiest way to do this is going to be to compare this to the parent function, which I'll do over here. In fact, actually, you know what? We'll call it p of x, because why not? So p for parent. So p of x is just simply the parent function for absolute value. So again, it's like the most basic possible absolute value equation. It's just absolute value of x. And if this were the case, if we were dealing with the parent function, the vertex of the graph would be at the origin, right? So as we've seen, the graphs of absolute value tend to look like a V, like this one does. This also looks like a V. Sometimes the V is upside down, right? This one's right side up. And it's no different than with the parent function. The parent function also looks like a V, and the vertex, the sort of like the lowest point, the point where the V kind of meets, is at the origin. But now we see that the vertex is not in the origin, it's in quadrant 3. And so essentially what's happened here is the parent function has been transformed into the current graph, the current function, and that we're trying to get the equation for. And so I think the easiest way to do this problem is going to be to think about, well, what are the transformations that happened to the parent function to now get us to where we are right now? And in order to do that, I think it's going to be helpful to think about, well, let's start with the vertex and sort of see how that moved. So if we're looking at the vertex, it was at 0, 0, but then it shifted to the left, right? 1, 2, 3, 4, 5, right? So my vertex shifted 5 units to the left. Now, as we've seen in a couple different contexts, when you're applying a transformation to a graph, not just an absolute value function, but really like any function, what happens to your input, which is x in this case, we're going to take x, and because we're going to the left, when you go to the left, you add the distance that you've traveled. So when we're going to the left, we're going to add 5. So it used to be x, right? The parent function was x, and now it's x plus 5. And that entire thing is going to be inside the absolute value. So we've replaced x with x plus 5. The next thing that we're going to look at, again with the vertex here, is it also looks like there's been a vertical shift. So from where we left off, we're going to go down 1, 2, 3, 4. And with a vertical shift, it's outside the absolute value, and because it's down, it's going to be negative. We're simply going to subtract. We are simply going to subtract 4 at the end. That represents a vertical shift. Now, the only other thing that we have to check here is, has this graph been like either stretched or shrunk or anything like that? And in order to evaluate that, I'm actually going to get rid of all this stuff here. In order to evaluate that, we have to look at what is the rate of change for this absolute value equation. So what I mean by that is from the new vertex, notice that in both directions we go up 1 over 1 to get there. And then we go up 1 over 1 to get there. We go up 1 over 1 to get there. Likewise on the left, it's the same thing, same thing, same thing. That is actually the same as the parent function, right? The parent function doesn't have a coefficient in front of the absolute value, or rather it's a 1, and so therefore it's invisible, et cetera, et cetera. That is also the case in this graph, right? This graph has not been shrunk or stretched or flipped. Literally all that's happened is we've shifted it left and down. But other than that, it's actually the same thing as the parent function. So we shift it left, we shift it down, we don't do anything else, we leave it the way it is. So actually what that means is, for number 8, this is our final answer. If there was any kind of like shrinking or stretching or flipping, we'd have to do something here, right? There would have to be some sort of a number, a coefficient on your absolute value. But because that doesn't apply to this question, because the rate of change is itself unchanged, it's just 1 over 1, 1 over 1, 1 over 1, we don't need to do anything in front of the absolute value, and so that is our final answer. Number 9. For number 9, we're being asked to make a table of values and be sure to include the vertex in the table. All right, so our given information is an explicit absolute value equation, and we're going to essentially represent this function. It's the same function, but now we're going to just represent it using a table of values. So for a table of values, we'll go ahead and we'll just go with x and h of x. That's the name of our function. All right. the directions here, they make a point of saying be sure to include the vertex in the table. Even if the direction, I mean, that's more of a reminder than anything else. Even if the directions did not say to do that, we would still want to do it, right? So it's like a quasi suggestion, but it's like kind of required in a way. Technically, the table doesn't need it, but you're going to want to include the vertex when you're talking about an absolute value function. It's an important point to include. So we need to figure out, all right, well, where is the vertex? And the vertex of an absolute value function occurs when the absolute value piece equals 0. So again, with an absolute value function, in order to figure out what x value result or gives you your vertex, what is the x coordinate of the vertex? The x coordinate is whatever makes your absolute value piece equal to 0. So with the parent function, right? So we'll use f of x this time, I guess. So with the parent function of just absolute value of x, obviously here, this is going to just equal 0. So x equals 0. But here with 9, this graph has been transformed from the parent function. There's been a number of different things that have happened to this. And specifically, because it's x minus 6, this graph, this function, has actually been shifted to the right 6 units. And so if we want the vertex, we're going to do it when x minus 6 equals 0. Well, this is relatively easy to solve. It means that x is going to equal 6. That's going to be the coordinate. That's going to be the x coordinate of our vertex. So I definitely want to include that as an input in my table, right? I want to include 6. Now, I think probably I'm going to get rid of all this scratch work here. All right. I think in order to get h of x, I honestly think that the easiest thing is just going to be to plug it in. We could sort of think of this in terms of like transformations and other stuff, but I think that's just more work than necessary. I say we just plug in 6 and sort of just see what we get. So I'll do this. I'm not going to do this for every single entry, but I'll do it for at least the first one, and then we'll see how much is going to be necessary. So we're looking for h. We are looking for h of 6, right? What is the result of this function when I plug in a 6? So we're going to get 5 absolute value. We're plugging in for x, so this becomes 6 minus 6, close absolute value, minus 8. All right. Well, remember, we're at the vertex, we want absolute value to equal 0, which is going to happen here because 6 minus 6 is 0. So we end up getting 5 times the absolute value of 0 minus 8. Well, the absolute value of 0 is just 0. 5 times 0 is 0. And 0 minus 8 is negative 8. Some of those steps you probably could have done in your head without writing them out, but I just wanted to kind of show you the full process of how we would do this. So anyway, you plug in a 6, we get a negative 8, which, oh, by the way, happens to be our vertical shift. That is not a coincidence. So technically, we didn't really need to do all that. We could just look at the negative 8, and that actually, theoretically, that alone is our answer, but it was good to, I think, evaluate it. Now, that's the vertex, but we can't really stop there. We got to include more points. You can't just have a table with just one entry. That's not going to work. So we've got to get some additional points, and although it's not a like super strict rule, it's probably a good idea to sort of start at the vertex and just sort of go to the left and go to the right. Okay, so we're kind of free to do any values we want, but it's going to be the most helpful if we go from the 6 and we go like 1 unit, 1 unit, 1 unit in each direction. So I would say that after 6, the next thing that we could do would be 7. Well, that's definitely not what we want to do. There we go. 7, right? Makes sense. This is going to be just 1 unit to the right of the vertex. I think I'll write this out I'll write this out one more time, but I am not going to write out every single one because that's going to get kind of annoying. All right. So we are looking for h of 7. Okay, h of 7. So that's going to equal 5, absolute value, 7 minus 6, close absolute value, minus 8. 7 minus 6 is 1. So 5 times the absolute value of 1 minus 8. Absolute value of 1 is 1. 5 times 1 is 5. And 5 minus 8 is negative 3. So you plug in a 7, you get negative 3. Notice that to go from negative 8 to negative 3, we add 5, which also happens to be the coefficient. That is not a coincidence. That is just another, I guess, observation. But that pattern will hold. Plug in an 8. This one I'm not going to write out, but it's going to be the same process as what you see in green, except you replace the 7 with the 8. So we end up getting 8 minus 6 is 2, absolute value of 2 is 2, 5 times 2 is 10, and 10 minus 8 is 2. Again, just in the interest of time, I'm doing this a little bit quicker. We'll do one more. I mean, there's no real super strict rule in terms of how many points to include, but we'll just do kind of maybe 3 on each side of the vertex. So again, we plug in a 9. 9 minus 6 is 3. Absolute value of 3 is 3. 5 times 3 is 15. And 15 minus 8 is 7. Notice that our h of x values are increasing by 5 every time, which, again, is because of that 5 right there. We're almost done, except I think it would also be good to include units to the left of the vertex. So that means what happens when we... That's the second time I've done that. 5. So we want 1 unit to the left of 6, which is 5. And if we plug in a 5, here's what happens. 5 minus 6 is negative 1. Maybe I'll write this one out, actually. So let's see what we get this time. So we're doing h of 5. So that means wherever I see an x, I'm going to plug in a 5, which is right there. And, okay. 5 minus 6 is negative 1. All right? So what's inside the absolute value is negative. But of course, when you take the absolute value of a negative, you drop the negative. So the absolute value of negative 1 is 1. And then 5 times 1 is 5, and 5 minus 8 is negative 3. So you plug in a 5, and you get a negative 3. And notice, it's the same value, right? So on either side of my vertex, my result is this negative 3. You know, you think about an absolute value graph, it looks like a V, right? So from the vertex, if you go to the left and you go to the right, it's actually very common to see this kind of pattern. For 4, 4 minus 6 is negative 2. Absolute value of negative 2 is 2. 5 times 2 is 10. And 10 minus 8 is 2, which also happens to be the same result from 8. And for 3, you know, if we follow our pattern, we quote-unquote know it's going to be 7. But if we want to evaluate it, 3 minus 6 is negative 3. Absolute value of negative 3 is 3. 5 times 3 is 15. And 15 minus 8 is, in fact, 7. So that is my table of values. Next assigned question was number 12. And for 12, I guess we skipped over the directions. Directions started with, directions started with 11. So the directions are here for the next section. Graph each of the absolute value functions. All right. So we can skip 11, go to 12. All right, so they're asking us to graph this. So g of x equals absolute value of x plus 4 minus 2. Now, again, there's a couple different ways that we can go about this. you can always generate a table of values, right? That's what essentially that's what graphing is. It's just it's a collection of points. It's a collection from a table. That's what a calculator does. It just creates a whole bunch of points. In this context, I actually think it's going to be easier if we're going to graph this. I think that it's going to be easier if we compare it to the parent function of simply absolute value of x. And if we compare the parent function to g of x, and if we sort of think about, all right, well, what were the transformations that happened to the parent function that is now giving us g of x? I actually think that thinking of it that way in the long run is going to make our job easier. One of the benefits of doing this is that this is going to work not just with absolute value functions, but with all different kinds of functions. You're going to learn about some weird I mean, there's logarithmic, all sorts of trigonometric. There's all sorts of functions where this process will work. So I think that thinking of what are the transformations that happened and then just plotting that. So if you take a look at g of x, there's been two things have happened to the parent function that now give us g of x. There's this plus 4, and then there's the minus 2. Right? You take those things away, you get the parent function. So what's happened is the vertex of the parent function is normally at the origin. Right? It's a v where the center point, the sharp point, if you will, is at the origin. When we look at our equation for g of x, the first thing that we have to sort of pay attention to is this x plus 4. Right? And the x plus 4 tells us that it has been shifted 4 units, and it's because it's x, it's either left or right, and because it's plus 4, when you see plus 4 like that, it's been shifted 4 units to the left. Okay? So it's been shifted 4 units to the left. So that brings us to, I'll do some scratch work. I'm going to end up erasing this. I guess we also have to think of a scale here. I think we can keep it at 1 box. I think we can just keep it as at 1 box. I don't think we have to double up here. So yeah, we'll keep it as 1. Oop, hold on. So our scale, we'll just keep it at 1, 2, 3, 1, 2, 3. All right, so each box is 1. So because our parent function has been shifted 4 units to the left, so from the origin, we're going to go, all right, 1, 2, 3, 4. And then the other piece here is the minus 2. And the minus 2 tells us this is a vertical shift, so it's going to be either up or down. And because it's minus 2, that means it's going to be shifted 2 units down. All right? So with a vertical shift, if the number is negative, you go down. So that means, again, from here, we're going to go down 1, down 2. And so now my new vertex for g of x, for the thing that I want, is right there. Now I'm just going to clean up this because we no longer need it. All right, so that's my new vertex. Notice that there's no other changes here. There's no coefficient. The other thing that you would probably see here is you could potentially see a coefficient in front of the absolute value, and we're not seeing that, right? So because there's no coefficient there, there's no stretching or shrinking or flipping or anything like that. So with the parent function, my rate of change is 1. It's 1 over 1, 1 over 1, 1 over 1. And that's actually still going to be true for my new function. We're still going to go up 1 over 1, up 1 over 1, up 1 over 1. So what that means is our graph from the vertex, we're going to go up 1 over 1, up 1 over 1, up 1 over 1, right? Just like that. And on the left, we don't have a lot of space, but we can still go up 1 over 1 like that. We'll have like a kind of a skewed V here. So I just need to connect my points here. So we got the little guy, that, and then we've got the big guy, just like that. And I think, we got, obviously that's X, obviously that's Y. I think that is everything. So that is the graph for g of x, the result of transforming the parent function by shifting it 4 units to the left and 2 units down. Fourteen has the same directions as 12. So we just got to graph this. So now our function is r of x equals 3 absolute value x minus 4 and close absolute value minus 6. So this is going to be similar to the last problem. There's going to be just really to like 1 or maybe 2 modifications, but it's going to be pretty similar. So again, just like before, we want to compare this to the parent function. So we want to compare this to the parent function for absolute value, which is just the absolute value of x, right? And again, with the parent function, our vertex would quote unquote normally, well, not quote, it is at the origin, right? So the parent function is a v that is centered at the origin, and it's just up 1 over 1, up 1 over 1, up 1 over 1. With r of x, we've had 3 things that have changed. We have x minus 4, which represents a horizontal shift. We have a 3, which represents a stretch. And then we have a minus 6, which represents a vertical shift. So, and the order that I just said them is the order that we're going to sort of deal with them. So the x minus 4, like I said, that's a horizontal shift. And when it's minus, like it is in this case, that tells us that we're going to go to the right. So x minus 4 means we have a horizontal shift to the right. And we're going to have to modify our scale a little bit here because it's not going to fit otherwise. So I think maybe we'll go with 2 boxes, I think should be sufficient. So we'll have a scale of 2, 4, 6, and 2, 4, 6. So I think that should be fine. See how this works out. So again, we're trying to place our vertex, and then from the vertex, we're just going to do whatever else it is that we need to do. So starting at the origin, which is where the vertex is for the parent function, we have a horizontal shift to the right 4 units. So that brings me, I'm not going to draw it on the graph, but it brings me to 4, 0. And then we do have a stretch of the 3. But actually, it turns out that that does not impact the vertex at all. So that 3 is going to basically impact every other point. But the vertex is actually unaffected by that. And the reason is because at the vertex, this piece becomes 0. So it actually doesn't matter what the coefficient is at the vertex because the absolute value piece becomes 0, and then anything times 0 is 0. So it ends up not really mattering for the vertex. We're going to ignore the 3 for now. And then we have a vertical shift of minus 6. That means we're going to go down 6 units. So when all's said and done, our new vertex, we're going to go from the origin. We're going to go right 4 units. We're going to go down 6 units, which puts us right there. All right, remember our scale is 2 for every box here. So we go to the right 4, we go down 6. That puts us at that dot right there in quadrant 4. All right, now we're going to think about the 3. Because what that 3 does is it basically it causes all of our y values, all of our function results, to increase by a factor of 3. So the parent function, the rate of change was 1, right? Because there's an invisible. Keep doing that. There's an invisible 1 in front of the absolute value, but now that has become a 3. So instead of going up 1 over 1, up 1 over 1 like the parent function, from our new vertex, we're actually going to go up 3 over 1. So from here, if I go up 3 over 1, that puts us right there. So we went up 3 over 1. If I do it again, if I go up 3 over 1, that puts us there. Up 3 over 1, up 3 over 1, up 3 over 1. Okay? And absolute value functions like this, linear absolute value functions, have a certain symmetry to them. Again, they tend to look like a V. So everything that we just did on the left, we're also going to do on the right. So again, from the vertex, if we go up 3 and to the right, we're right there-ish. It's a little hard when it's kind of floating in between the boxes. Yeah, that's better. Again, up 3 to the right 1, up 3 to the right 1, up 3 to the right 1, up 3 to the right 1. And we connect these points, and we should be good to go. So let's see. So that's first piece there. And my second piece is right there. And that is the graph of R of x. No, hold on. I skipped one. I went too far. Okay, 15. Yeah, we need the directions anyway, and we have to do 15. All right, so next assigned problem is 15. The directions here say use the given graph of an absolute value function to write the equation for the function. Okay, so we have a graph. We want to know what is the equation here. And we want our equation to use absolute value. We could write an equation here using a piecewise function, but given the context of the directions here, they're saying it's an absolute value function, so our equation really should be involving absolute value. Even though we could use a piecewise in this situation, it makes sense to use absolute value. So let's go just f of x, why not? And again, we've seen this now in a couple problems. I think the easiest way to do this is going to be to compare this to the parent function. So p of x is just the absolute value of x. And we know that with the parent function, our vertex is at the origin. And it's up 1 over 1, up 1 over 1, up 1 over 1, just like that. Right? So that's what the parent function looks like. And clearly this graph, it's not terribly different from the parent function. It certainly has some similarities, but it is obviously different. So we got to figure out how do we express those differences? How do we express those transformations in our equation? Well, if we follow sort of like the journey that our new vertex took to get to where it is now, from the parent function, what happened with the vertex? Well, you can see that starting at the origin, in order to get to the new vertex, we have to go to the left 1 unit, right? So from 0, 0, we go to negative 1, 0. And when you have a horizontal shift like this, that tells us that we have taken our input, which is x, And because we're going to the left, it means we add 1. So in the parent function, you have x, and in our new function, you have x plus 1, and that is inside the absolute value. We've replaced the x with an x plus 1. We also, in order to get to our new vertex, we also, from here, we have to go down. We have to go down 1, 2, 3. That's a vertical shift. In order to represent a vertical shift in our equation, outside of the absolute value, sort of at the end, we want to subtract 3. With a vertical shift, when you go down, that means it's negative. So you want to subtract 3 at the end. Now, we're kind of done looking at the vertex, so I'm going to get rid of that. The other thing that we have to check is to see, all right, has this graph been flipped or stretched or shrunk in any way? And from my new vertex, notice that on the right, I go up 1 over 1. I go up 1 over 1. I go up 1 over 1. On the left, it's the same thing. I go up 1 over 1, up 1 over 1, up 1 over 1. That is the same as the parent function. The parent function is also up 1 over 1, up 1 over 1. So that means that there is no number here that we need to write. We can keep that number as an invisible 1. Right? We're not going to say 1, but it is there. But the point is that we don't have to replace that with some other number in front of the absolute value, because there's been no stretching or anything like that. So that means that this is our final answer for number 15. Looking at 16. Again, we have a graph of an absolute value function. We want to write the equation. We want our equation to also use absolute value. We don't want to express this in a piecewise manner. And just like before, we are going to start by comparing it to the parent function. You know what? I'm going to write it like this. I'm sick of changing it back and forth. So there you go. So we're going to compare this to the parent function, p of x equals absolute value of x. In the parent function, our vertex is, as always, at the origin, at 0, 0. And again, pretty clearly, this vertex is not at the origin. It's in quadrant 1. And so in order to get from my previous vertex with the parent function to my new vertex for this function we'll call it, we'll mix it up a little bit, we'll call it g of x. So this function we're just going to call g of x. So in order to get to the vertex for g of x, from my old vertex for the parent function, the first thing we want to do is we want to look, all right, has there been a horizontal shift? Have we moved left or right? And the answer is clearly yes, we've moved to the right. So specifically, we've moved 1, 2, 3 units to the right. What that means is we're going to take our parent function and we're going to replace x with x minus 3. With a horizontal shift, when you go to the right, it's minus. So instead of saying absolute value of x, we're going to say absolute value of x minus 3. We are replacing the x with an x minus 3. All right, so that means we have a horizontal shift of 3 units to the right. The next question that we need to ask ourselves, at least in terms of getting to our new vertex, is has there been a vertical shift? Have we gone up or down? And again, the answer is clearly yes, we've gone up. So what we want to do is we want to continue our sort of journey here, and we're going to go 1, 2, 3, 4, 5, 6. Okay? So what that means is we've had a vertical shift up 6 units, and in order to reflect that in our equation, at the very end, it's almost like as an afterthought, you're like, da 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 da. Oh, and also, by the way, guys, add 6. Like when you're quote unquote done with like whatever it is that you're doing on the left, just take your result and add 6. That is a vertical shift up 6 units. Now, that gets us to the vertex. Right? So that sort of establishes that point right there. But we're not done because, again, I'll change it down. With the parent function, first of all, it's a v that's going up like that. That's the parent function. And the rate of change for the parent function is up 1 over 1, up 1 over 1, up 1 over 1. In this graph, there's been two more changes that we haven't yet accounted for in our equation. First of all, it's kind of obvious, but this thing's been flipped, right? The parent function is a v going up. This is a v going down. And so in order to reflect that change, we're going to have a negative on our absolute value, on the outside of it, right? So you take x minus 3, you get the absolute value, but then your result becomes negative, okay? So that will flip the v from going up to going down. And in general, not just with absolute value, but whatever the graph is, when you do something like this, you will flip the graph vertically, okay? Not just with absolute value. All right, so that gets us to an upside down V. But now, if we continue to sort of investigate this a little bit more, notice that from my vertex, if I go to the right, notice that I go down 2. Oof, hold on. Notice that from my vertex, if I want to proceed on the right, I go down 2 and over 1, right? With the parent function, vertically we travel 1 unit and then we go over 1 unit. But now with this function, our vertical sort of traveling is 2 units and then over 1. And that continues, down 2 over 1, down 2 over 1, right? If I go to the left, it's the same thing, down 2 over 1, down 2 over 1, down 2 over 1. And so not only has it been flipped, but it's also been stretched by a factor of 2. So now I'm just going to write this. So this is a negative 2. I'm just going to rewrite it as negative 2, just like that. And let me get rid of all this kind of scratch work here. That should be our final answer. So to recap, we took our parent function. We have a horizontal shift to the right, 3 units. We have a vertical shift up, 6 units. And we have a stretch, actually, sorry, I'm going to be a stickler here. The order that you describe these things actually does matter. And the order is you need to start with your horizontal shift. So for this graph, we had a horizontal shift to the right 3 units. Then the negative 2 kicks in, which means our graph flipped vertically and was stretched by a factor of 2. Then we have a vertical shift up 6 units. So it's horizontal shift, then stretching and flipping, then the vertical shift describes the full set of transformations for number 16. All right, we'll wrap up this assignment in the Go section. And there's only one set of instructions here for the Go section. Rewrite each expression by performing the indicated operation. Each new expression should contain only one square root. All right, so they're being rather specific here about what our answer should look like. And for all of these, whenever we give our final answer, there really should only be a single square root in it. So let's keep that in mind. First assigned problem was 17. So with 17, just make sure all my markers are ready to go here, and they are. Good. Okay. So with 17, I'll just read it out. So for 17, we want to simplify parentheses negative 7 minus 2 root 5, close parentheses, plus parentheses, 6 plus 8 root 5, close parentheses. So we're adding two numbers that have a constant, two numbers that each of them comprise an integer, so negative 7 and 6, and an irrational number, 2 root 5 and 8 root 5. So again, you can think of this as like one number plus another number, and each number has two parts to it, right? And each of these numbers has an integer part and it has an irrational part. It turns out that our answer will actually look like this. Our final answer is going to look like an integer part and an irrational part. So when you're working with this kind of problem, I think the easiest way to start is actually to remove the parentheses. So sort of no longer see it as like two numbers, but just sort of like get rid of the parentheses and just treat it as like a whole bunch of terms that we're going to combine. You want to remove the parentheses, and removing the first set of parentheses is relatively easy because they literally just go away, right? So the first set of parentheses, you just drop them, and this becomes -7 minus 2 root 5. Notice that nothing changed. I just got rid of the parentheses. Now, with the second set of parentheses, this may or may not be easy or straightforward. If you are adding the second number, if you're adding the second number, you can safely drop the parentheses and not change anything. All right. So for 17, this first step is in fact relatively straightforward because we're adding the second number, and when you're adding the second number, you are free to just drop the parentheses and just write what's inside, which is plus 6 and plus 8 root 5. Now, if the problem was minus, which, spoiler alert, we're going to see with 18, if the operation in the middle was minus, we would have to distribute that minus, and we'd have to be careful about our signs, okay, changing all of our signs. But that was not the case for 17, so our first step is to just drop the parentheses, and now we have this sort of like hodgepodge of terms. And our really second and I think final step here is going to be to just simply combine like terms. So you can treat the root 5 like an x, right? So if you think of what this would look like, I'm going to write this, but then I'm going to erase it. If you have -7 minus 2x plus 6 plus 8x, well, you would combine the -7 and the 6 to get -1, and you'd combine the -2x and the 8x, and you'd get 6x. Right? That's how you would simplify this algebraic expression. So what we're going to do here is basically the same exact thing. You're going to treat the root 5 just like you would treat a variable or an unknown. So our integer parts are -7 and +6. We can combine those. -7 plus 6 is -1. We can also combine our irrational parts, and the irrational parts are -2 root 5 and 8 root 5. So if you have, -2 of something and you add 8 of that something, you just combine your coefficients. So -2 plus 8 is 6. And just like you would include the x here, we're going to include the root 5 because we have 6 of them. We essentially have 6 root 5s, if you will, right? So, and also, I guess technically we should have just checked that we cannot simplify root 5. We can't, right? So root 5 is as simple as it gets, which means this is our final answer. And again, as predicted, our final answer looks like one of the two original numbers where you have an integer part and you have an irrational part. 18. 18 is going to be very similar to 17 with just one relatively small wrinkle that we do have to deal with. So again, with 18, we've got these two numbers, and each number contains an integer part and an irrational part. And this time we are finding the difference of them. We are subtracting them. Just like with 17, our first step, I think, should be to just remove the parentheses. And the first set of parentheses, again, just like 17, you can remove the first set of parentheses without too much trouble. So they just go away, and you're left with -10 minus root 13. Now, The middle operation, right, the thing that we're doing to these two numbers that each have two parts to them is we are subtracting them. What that means is we have to distribute that negative to both terms inside the second set of parentheses because, again, we're subtracting the entire thing. That's what the parentheses are doing. The parentheses are saying subtract all of it. So when we remove the parentheses here, we have to distribute that negative, which means all of the signs are going to change inside that second number. So the original integer part of our second number was negative 11. However, because we're subtracting it, what we're really doing is we're subtracting a negative 11. And when you subtract a negative, you're really adding, right? So this becomes plus 11. Likewise, the irrational part of our second number was 5 root 13, and we were adding it. It was positive, but now we're subtracting it. So when you subtract a positive, you're subtracting. That's what that means. So we are now subtracting 5 root 13. All right. Now all we have to do is just combine our integer parts, combine our irrational parts, and then we're done. Also, as a side note, the square root of 13 cannot be simplified. 13 is prime. So anytime you have a prime number underneath a square root, yeah, that thing is not going to get simplified. So 13 is prime, and so there's nothing we can really do there. So this simplifies to negative 10 plus 11. Right? We're combining our integer parts. Negative 10 plus 11 is positive 1. For the irrational parts, we have negative root 13 minus 5 root 13. And again, if you treat the square root as an x, well, there's no number in front of the first 13, but there's an invisible 1. Right? There's like always an invisible 1 anytime you have a term like this. And so this is really like 1 times root 13. So we have a negative 1 minus 5. And if you think about what this would look like with x's, well, negative 1x minus 5x is going to equal negative 6x. Right? So we're going to apply that same concept to this. Negative 1 root 13 minus 5 root 13 is negative 6. Oop, redo that 6. Is negative 6 root 13. Just like over here, you'd have negative 6x. Well, now it's negative 6 root 13. And like I said, we can't simplify the square root of 13, which means that is our final answer. Last question is number 20. So with 20, the directions don't change, but it's a different kind of problem than 17 and 18 because, well, I mean, it looks different, right? So for 20, we have the square root of 98 plus the square root of 8. Now, we can't, remember, the directions say you should only have one square root. So we got to do something here. The problem is that as these things are currently written, we can't combine these into one square root. There's no real way to combine the square root of 98 with the square root of 8. So we're kind of stuck with these two square roots. So in order to simplify this down to one square root, what we need to do is we need to rewrite both of these. So we'll do it down here. We need to rewrite both of these so that we can combine them. All right? Now, this is essentially what we're going to be doing here is we're going to be simplifying these square roots. And when you're trying to simplify a square root, I found that I think the easiest way to do this is, and I'm not saying it's easy, but it's easier than I think other methods, is to figure out what is the largest square number that goes in evenly into 98. All right? So again, we're looking for what is the largest square number that goes into 98. Now, that's not going to be very helpful unless you know what a square number is. Square numbers are the result of taking an integer and squaring it, right? So technically 1 is a square number because 1 squared is 1, but we're going to skip that for right now. 2 squared is 4, which means 4 is a square number. 3 squared is 9, which means 9 is a square number. 4 squared is 16, so 16 is a square number. So this continues. 25, 36, 49, skipped one, 64, 81, 100, and so on, right? This is an infinite list, obviously. But every single number that's in a box right now, that's a square number. And what we want to do is we want to figure out which of these, and this continues indefinitely, which of these is the largest that I can divide evenly into 98. Right? Now, I would encourage, if you're kind of unsure how to do this, you can take your calculator, if you have access to a calculator, and you can try taking, all right, well, what's 98 divided by 100? That's a decimal, that doesn't work. What's 98 divided by 81? That's a decimal, that doesn't work. What's 98 divided by 64? That's a decimal, that doesn't work. However, 98 divided by 49 does work, and then your other factor here is a 2. And that's easy enough to check because 49 times 2 is 98. Okay? So what we've done is we've found the largest square number that goes in evenly into 98. That is 49. And we have a 2 as well left over. 2 is not a square number, but that's fine. And what we can do here is we can take our big square root and we can break it up into 2 square roots. Right? We are allowed to do that mathematically. And our 2 square roots now are being multiplied. So we took the big one, broke it up into 2. And what's nice about this is that if you do this correctly, the first square root, which is the square root of 49, well, the square root of 49 is 7. It's an integer. It's a rational number, right? So root 49 simplifies to 7. And then this root 2 is still sort of like trapped under the square root. Can't really get out. So the square root of 98 simplifies to 7 root 2. All right. We're going to do the same thing with the square root of 8. So for the square root of 8, to simplify any square root, again, what is the largest square number, times some other number? What's the largest square number that goes in evenly into 8? Well, okay, this number has to be less than or equal to 8. It doesn't make any sense actually to start with a number above 8 because if the number is larger than 8, it doesn't go evenly into 8. So we don't really have a lot of choices here. We kind of have to go with 4. But luckily 4 does go evenly into 8 because 4 times 2 is 8. So that means that we can break this up. We can break this up into the square root of 4 and the square root of 2. Again, what's nice about this is that the first number is an integer. The square root of 4 is 2. And then again, the other 2 here stays underneath the square root. This is going to work out pretty nicely for us. The reason is because the square root of 98 we just said is 7 root 2. We're adding the square root of 8, which we also just found is 2 root 2. Now, notice that we have an identical square root in both terms. It's root 2 and root 2. And again, if you think about what this would look like, if you had 7x and you added 2x, well, you'd get 9x, right? That's easy. If you take a look at what we have here, We have 7 root 2 plus 2 root 2. It's the same thing. It's the same thing as with an x. So 7 plus 2 is 9. And you have not, what do you have 9 of? Well, they're root 2. So you have 9 root 2. And that is our final answer.